Our next speaker and topic is engineering advances in quantum technology, Dr. Jay Lowell from Boeing. Dr. Lowell is chief engineer of Boeing's Disruptive Computing Networks and Sensors, which leverages core technologies in quantum communications, computing, and sensing, neuromorphic brain-inspired processing, high-performance computing, and advanced networking to develop computing and communication solutions for advanced commercial and government aerospace applications. Please join me in welcoming Dr. Jay Lowell.
So now for something completely different. All right, so let me start off by talking about our 107-year-old startup. We're a company that builds a lot of things and does, mostly that's airplanes, satellites, anything that moves and brings people together. Our mission is to connect the people of the world. Boeing is formed of a merger of about 10 other major companies and probably dozens of other smaller companies over time in its 107-year history that are organized into 3 or 4 main business units. Commercial airplanes group, which most of you hopefully flew here on. Defense, space, and security, which provides products to governments around the world. Global services, which basically feeds those people who take care of those products that we sell, and actually other people's products. And then the Boeing Capital Corporation, because airplanes, it turns out, are a little expensive, we help people finance our products, the purchase of our products. Where we sit, where I sit, and kind of I'm doing this to give you a sense of what it is that we're doing and why Boeing is doing this stuff at all. We sit in a function called Engineering, Tests, and Technology, which provides all of the engineering for everybody around those 3 business units. And within that group, there is a research and technology organization and our small little organization, Disruptive Computing Networks and Sensors. We are what I like to call a deep tech incubator. You heard about some of the things that we've been focused on over time. Right now, we are focused on 2 areas of technology, quantum technologies and high-fidelity digital twins. Those high-fidelity digital twins are how we are able to more rapidly test our products in a manner that helps us understand the effectiveness of the hardware and software without having to field that in expensive flight tests. So what I'm going to do today is talk to you about a smattering of all of the things that we're doing. And this is kind of the landscape of the projects that we have, or at least most of the landscape. It's the part that I'm going to be able, that I can talk about that we're doing. There's one other project on here that should be on here, but I can't talk about that until next year. Our projects really are across the board. Our goal and our look and our view of quantum technologies are, this is something that we need to look at with an eye towards the long term. The company, having developed commercial airplanes and having developed military products, we think in long time cycles. The development of a commercial airplane project is a 15 to 20-year endeavor. So we're trying to apply that kind of long-term strategic thinking, which means we need to be aware of and understand the implications of quantum sensing, computing, and networks. And so we've stood up projects that allow us to develop capabilities, investigate what can be done in these spaces, learn, get people, training, all of the things that we need to have to eventually be successful when we are ready to productize the output of this research. So right now we're focused on essentially demonstrations and prototyping projects with an eye towards eventually developing products and services for the company. Today I'm going to talk about 3 of these 7 projects that you see. I'm going to start talking about our quantum system microelectronics project. I'll then pivot to talk about our qode project, which is in conjunction with HRL Laboratories. HRL Laboratories is a partially owned subsidiary of the Boeing company, and we share that ownership with General Motors. We collaborate with them frequently because of that long-standing relationship. And then I'll end talking about work in our quantum navigation unit. I apologize, they're going to be just sudden jump cuts. This is not kind of a constant one theme talk. We're really going to jump around and talk about each of these three things in just enough depth that you'll be wanting more, and I will have probably exhausted what I'm willing to say. So let's get started. So let me talk about my microelectronics project. This project is because we recognize that in order to build quantum systems, we need control systems. We need electronics, and those electronics have very demanding requirements for what they have to do, whether they're working on helping a quantum network, a quantum sensor, or a quantum computer work. So we looked around at all of these areas and use cases and said, what are the most demanding electronics needs? They end up being in the computing case right now. Actually, there are a similar number of demanding applications in the networks space, but the definition of those was not sufficiently rigorous that we could focus the project around this. So what we did was we have chosen, in order to focus on developing a core electronics capability that can be applicable to quantum projects, we have decided to look at a particular computing use case and develop cryogenic electronics to support that use case. Again, as you see, the goal here, although the project is focused on doing that today and for the near term, our goal is to develop a capability that we can then redirect and redeploy towards any of these potential hardware projects that we might need to build in the future. Like I said, we're trying to take a long-term view to this capability. So our goal as a project and our objective is to develop and demonstrate a cryogenic by design ASIC capability so that we can produce an ASIC, custom ASIC, that produces all of the functions needed to control a qubit in a cryogenic environment, and do that so that we design it, it has the performance that we specify in the design, and when we test it, that's what it delivers. We're doing this using GlobalFoundries 12LP process, so it's state-of-the-art, advanced technology node silicon process. This chip has digital, analog, and RF components, and we understand and have been very focused on making this a cyclical process that's going to end up leaving us, again, with capabilities that will last far beyond the actual design of the chip that we have. For instance, we have focused this project on producing replacement PDKs for foundry PDKs that operate at 4 Kelvin in order to ensure that we're doing the design for the chips properly. We are modeling the interaction of the electronics with the qubit system, our target qubit system, to ensure, again, that we have traceability between the requirements that we specify for the electronics and the actual performance of the target system. As I said, we've worked on replacing the process design kit. That means we've had to develop test capabilities in-house and test actual transistor curves at 4K and use those to replace those device models that the foundry provides us and that we would then use in our EDA tools to design the circuits. We have this quantum model-based engineering platform that actually simulates the hardware, simulates the qubit, and actually is done in a form that allows us to extract specific electronic system requirements that are key, again, to tying this whole process together. And then we have the test infrastructure that allows us to put the chips that we devise and develop and produce, test them, validate their performance, go back, refine those models until everything works in a seamless process as well as we want. I'm happy to announce today that we have recently taped out a fabrication of a single-channel RF control qubit, cryogenic qubit designed to operate at 4 Kelvin. This is designed to operate one of those HRL projects, the qubit produced by one of those HRL projects, a single-spin Zeeman qubit. And we will also are working with a partner at the University of Texas, Austin, and we'll install this controller to control their superconducting qubit in their system. That chip, which we call Amundsen, we get back from fabrication. It's not next month, it's not yet October. We get that back the first week of November. So we look forward to showing results of that chip, how it performs, and demonstrating that controlling qubits next year. So that's my electronics project. As I said, I'm going to now jump. Now I'm going to talk about our qnode project. This project is a different focus, right? We're working in the quantum communication, quantum networking space. Our goal in this space is to understand what it takes to build the components that that together form the node of a entanglement-based quantum communication network, and integrate all of those components into a single photonics platform in order to make those repeaters something that is manufacturable, scalable, and deliverable to customers. So to do this over the period of time, we've demonstrated things like entangled biphoton sources to produce entangled photon pairs, Bell state measurement devices, integrated cryogenic detectors, and the ability to produce a long lifetime quantum memory in the photonics system. To do this, we've focused on silicon carbide on insulator as our material platform. In the end, I'm not going to talk about the challenges that we saw in other material systems, but rather focus on the fact that when we look at the key properties that we see as necessary for all of these various components that end up being integrated into these kinds of devices, silicon carbide on insulator tick the box in just about every one of these things except that thin film uniformity. So we've spent the past year addressing that thin film uniformity problem. And I'm happy to say that we think we've licked that problem now and actually are going to be able to start producing devices that matter. First, on the left, before I talk about the thin film problem, I mentioned that we actually have demonstrated long life qubits. Here we've demonstrated color center emission and manipulation of essentially a single color center qubit in a silicon carbide on insulator material system, and captured that emission in a waveguide on a silicon carbide on insulator chip. We've also demonstrated the construction of linear photonic devices, including the deposition of superconducting nanowire single photon detectors on silicon carbide on insulator waveguides. And lastly, when I talk about this thickness variation, the issue here turns out to be a really deep and challenging material science problem, in that the way silicon carbide on insulator reacts with most mechanical and etchant approaches in your classic semiconductor manufacturing flows created surfaces that were either widely variant over the course of over the size of a wafer, or extremely rough. And we think we've licked that problem. We've demonstrated a 7x reduction in thickness variation over large areas, and on a process that we believe scales to wafer size. And actually, that's one of our demonstrations for this next year, will be to demonstrate this process on a wafer scale demonstration. So again, great accomplishments that we're happy to show here, that we think put us on a path towards the development and understanding of what it takes to produce integrated photonic devices necessary to operate quantum networks. Again, jump cut. So now we're going to talk about our quantum navigation project. And so what I thought I would do here is start off by really understanding why it is that we're doing what we're doing. Navigation is a tricky problem in the end, and no matter what anybody tries to tell you, if they're up on a stage and they tell you that their navigation technology solves all navigation problems, they're lying to you through their teeth. And so I'm not here to tell you that that's what we're doing. I'm here to tell you why it is we've chosen the particular technologies that we have, what we feel they address, and what we feel they don't address, because in the end, every navigation system is about putting multiple things together, each of which addresses the weaknesses of one of the other parts of the system. So in the end, fundamentally, navigation, you have a couple of strategies for how to figure out where you are and what you're doing. The first is to try to keep track of how you're moving. That's a really simple strategy, right? I measure velocity, acceleration, rotation, and I kind of build up a path of where I was from a point in time. The problem with that is I'm making a lot of little measurements and I'm adding them to the measurements that I did before. And so any errors that I have compound in the system and grow over time. And there's no way to bound those. They just grow. You can't undo those errors once they're in your solution. The only way you can address improving that is to make your measurements better, to improve your measurement precision. But again, you're limited, your error is going to grow. So how do you fix that? Well, GPS chose a different approach. They chose, sailors chose a different approach a long time ago, which is you orient to fixed points. They took measurements of angles to the stars, which were, once you correct for time, those stars are essentially in known positions. And when you determine your angles to those things, you have some idea of where you are. You don't necessarily know how you're moving, but you know where you are. Turns out the error characteristics, because you're dealing with angles and lots of, it's a complicated shape that essentially means that you have some challenges making that propagate through and looking at reliability. How you improve that, again, precision helps, but also making and using more references helps. GPS chose the third approach, that is range to a set of fixed points. GPS works as a system by taking time measurements of a signal that is arriving from satellites which are in positions that we can effectively say, at this particular time, that satellite is this location. I received that signal at this point in time, therefore I'm that far from that satellite. When I calculate that distance from a bunch of different satellites, then I can localize myself. It produces a uniform error characteristic, meaning that each time I do a measurement, I get nominally the same error in where I am, but it's relative to where I am. And that, again, the improvement strategy there is more references and improved timing. This is why you hear people commonly talk about clocks as being one of those things that can help precision navigation and timing. It helps with the timing. That timing, the more precisely I can do that timing, the more precisely I can determine my distance. And then last is I have map matching. Again, this is a pretty simple idea, but basically I look at some map and I basically figure out and correlate where I have been and measurements that I make against that map, whether it's looking at an image and saying where am I on that image, whether it's looking at a measurement of gravitational field, elevation, magnetic field. It doesn't really matter what it is as long as you have a map of it and you can make measurements of that thing, you correlate, you figure this out. Quantum technology really in the end allows us to address several of these things, and we've been focused on the three that are there on the right. Inertial measurements, ranging measurements, map matching. Our clock project I'm not going to talk about, but what we have done and what I'm happy to announce today is that we have completed the world's first tests of a quantum inertial navigation sensor that is a full 3-axis, complete degrees of freedom of motion quantum inertial measurement unit. In a ground test, we actually also completed a flight test with a single-axis inertial measurement sensor and a quantum magnetometer that we worked with. We've partnered with two companies who have a long history, well, some a long and some a shorter history, but have immense capability at the sensor development. That is AOSense on the inertial sensors and Sandbox AQ on the magnetic sensors. We've produced over 5 hours of flight test data And we are actually going to conduct a follow-on test with a full inertial measurement unit in January. This is a world's first demonstration. Nobody has ever accomplished this in the world. We're happy that we've outcompeted every government in the world, and very proud of the fact that we've been able to do this. And think that it is just one of those things where we are showing that in the end, quantum technology is useful when you're able to put it to its intended use. And in this case, we have to take the quantum technology out of the laboratory, put it on the platforms where we're going to go use it, and make the measurements that understand and tell us how the systems are going to work for us at the time that we need them. I hope that you've learned something today. I hope that you've found this an interesting example of the kinds of engineering challenges that we're trying to address in our quantum technology projects at the Boeing company. And I thank you for your time.